We're now looking at some exam questions regarding the topic of power. The first is from a November 2009 paper 41, question 1. It says a car of mass 1000 kilograms moves along a horizontal straight road passing through points A and B. The power of its engine is constant and equal to 15,000 watt. The driving force exerted by the engine is 750 newtons at A and 500 newtons at B. Find the speed of the car at A and B, and hence find the increase in the car's kinetic energy as it moves from A to B. So you are given information about the power, and you are also given information about the mass of the car, and you want to calculate speeds and then kinetic energies. So you have to use, obviously, the formula that relates power to speed. Okay, the power is always equal to the driving force times the speed at a given moment, which means that the speed is always the power divided by the driving force. So at A, you have all the information here in the diagram. At A is going to be 15,000, that is the power divided by the driving force at A, which is 750, that's 20 meters per second. At B is the same 15,000 watt, it doesn't change, divided by the new driving force, is 500 newtons, which is 30. Now that you have these two values, just use the formula for the change in kinetic energy, substitute everything in the right place, and you have here the result. How many points for this simple question? Let me just check. 4. Okay, another 4 points for this question 1. This is from spring 2010, question paper 41. A car of mass 1,150 kilograms travels up a straight hill inclined at a 1.2 degree to the horizontal. The resistance to motion of the car is 975 Newton. Find the acceleration of the car at an instant when it is moving with speed 16 meters per second and the engine is working at a power of 35 kilowatt. I've wrote all the numerical information again over here, and I made a diagram. Okay, you have a small inclination now. What do you have now? You have the driving force, which you can calculate because you are given the power and the speed. Okay, and you know that the driving force is going to be the power divided by the speed. All right. You know that there is a friction. Since it is going up a slope, you have a tiny, but it's there, horizontal component of the weight, and then you have the vertical component of the weight and the normal contact force, which you don't need for this question. All right. What you need is the value of the acceleration, and just apply Newton's second law to the horizontal axis. You know that the driving force minus the friction minus the horizontal component of the weight equals the mass times the acceleration. All right. This can be calculated the way I told you. Everything else is given. So it's just a matter of substituting the values and calculate the whole thing for A. Another 4 points, very simple. Spring 2012, question paper 41. Now question 3. You have this diagram that says a load of mass 160 kilograms is pulled vertically upwards from rest at a fixed point O on the ground using a winding drum. The load passes through a point A, 20 meters above O, with a speed of 1.25 meters per second. Find for the motion from O to A the gain in the potential energy of the load and the gain in the kinetic energy of the load. It starts from rest, don't forget. Okay, so these two are very, very simple. You just apply the formula, all right? The change in GPE is mg, and the change of height, it starts from 0. The height at A is 20, so that's 32,000 joules after substituting everything. The change in kinetic energy is 1/2 of m, the speed at the end square minus the speed at the beginning squared. This is 0. You have everything there, so the change in kinetic energy is 125 joules. Then it says that The power output of the winding drum is constant while the load is in motion. Again, the power output allows you to calculate the driving force. Given that the work done against the resistance to motion from O to A is 20 kilojoules and that the time taken for the load to travel from O to A is 41.7 seconds, find the power output of the winding drum. Okay, so what do we have and what do we need? We are given the work done by the frictional forces. We are given the time and we want the power. The power is what? Is the work done by the driving force divided by the time. How do you know you are going to use this formula? Because you are given the time. It's a good hint that you have to use the formula. The power from the engine, from the driving force, equals the work done by the driving force divided by the time. You know the time, the only thing that you need to calculate is this work. And for that, you use the main equation of this chapter. The work done by the horizontal force equals a change in kinetic energy. What is the work done by the resultant force? It is the work done by the driving force, which is the thing that we want. The work done by the friction, which we have. The work done by the force of gravity, which is the change or minus the change in in GPE, which we also got before, and the change in kinetic energy, which we also got. So we have everything. Okay? Don't forget, this is going to be a negative value, it's taking energy out of the system. This is going to be a negative value, it's taking energy out of the system as it goes up. This is going to be positive, as we can see over here. And this is going to be whatever it is. Okay, just substitute by the values over here. And you get here the work done by the driving force, divide by the time, and you have the power. One more. 2013 spring, paper 41. It's now question 4. A train of mass 400,000 kilograms is moving on a straight horizontal track. The power of the engine is constant and equal to 1,500 kilowatts, and the resistance to the train's motion is 30,000 newtons. Find first the acceleration of the train when its speed is 37.5 meters per second, and then the steady speed at which the train can move. Okay, let's make a very quick diagram of what's going on. I actually bothered to draw a small train, but you can treat this as a point mass. You have the driving force, you have the frictional force. It's in a horizontal leveled position, so you don't have to worry about the weight. This means that the driving force minus the friction equals the mass times the acceleration, right? We know the mass, we know the friction. The only thing that we are missing is the driving force. For that, you have to use the fact that you have the power and you have the speed. You have the power and the speed. You can calculate the driving force is the power divided by the speed, 40,000 newtons. Okay, so now you can just rearrange the formula, substitute by all the values, and you have the acceleration. What was the second question again? The steady speed at which the train can move. What is this steady speed? Okay, right now the train was moving with this speed, all right? But as the power doesn't change, as long as you have a driving force, the train is going to keep speeding up, right? But as it speeds up, what is going to happen to the driving force? It goes down because the power is kept the same. So if this one goes up, this one goes down. Eventually, this is going to be down up to the level of the friction, in which case it won't accelerate anymore. It reaches a constant velocity. So the force that you are going to use to answer this question is the force, the driving force that happens when it equals the friction. All right? So now the power is constant and equal to the same value. The power doesn't change. The only thing that changes is that the driving force now went down to correspond to the value of the friction, which you have over there. All right? So what is the speed? The speed equals the power divided by the driving force. The power is 1.5 times 10 to the power 6. The driving force is equal to the friction, so 3 times 10 to the power of 4, so the speed is 50 meters per second. That's the maximum speed.